To welcome Wei Kang, as I have known Wei for I don't know, maybe 23, 24 years. He's
Yeah.
my PhD advisor, and so yeah, today we'll be talking about topics at the intersection of deep learning and control theory. Yeah. Thank you.
Okay. Thank you, Boumediene, for the introduction, and thank you for the invitation of giving this talk. I'm glad to be here. And good morning, everyone, or good afternoon, depending on where you are. So today I will talk about the topics that relate to deep learning and control theory. These two fields historically share many common interests and common ideas. For example, if you look at this book that published 70 years ago. In this book, this is a book written by Nobel winner. Several concepts like control, neurobiology, computing, information, these concepts were treated by Weiner as different aspects of the same subject, which he called it cybernetics. The idea was to develop a highly interdisciplinary field that is applicable to both machine and animal and human being. So after so many years of development, these concepts have their own field, like control theory, information theory, artificial neural network, scientific computing, right? So the collaborations among scientists from these fields and the interaction between these fields created a huge literature. So when I say, the topics at the intersection of deep learning and control theory, by no means I can give you a complete review of these topics. Okay, not at all, not even close. All right, so I would just discuss a few papers that I happen to came across in my own research and in my communication with my colleagues. So I group these topics into three kind of categories. One is deep learning for control. So the idea is that how can we use deep learning to solve some control problems, especially those problems that is difficult or impossible to be solved using traditional control system design methodologies from control theory. Then another group of papers I would discuss a little bit is related to control theory for deep learning. Say the idea is that control theory or in general dynamic systems that has been studied for so many years with fruitful research. So can we take advantage of that to improve training, to design better neural networks? Okay. Then the third topic I'll talk about here is why does deep learning work for high dimensional problems? Well, this is a huge question, obviously. This is a huge question. There are more open questions than what we know. So here I will probably narrow down my discussion to a couple of, I think still kind of a preliminary ideas that we explored lately. Try to partially answer this question, but however, rather than dealing with different subjects like regression, dynamic system, and optimal control separately, we try to deal with these subjects collectively using a kind of a unified theoretical framework of approximation theory for neural networks. Okay, so that's the outline of the talk. So let's go to the first part of the talk, the deep learning for control theory. If you have a control system design problem, okay, then you face challenges. Well, you can group categorize these challenges in different ways. Here, for the sake of a discussion, I group them into three categories. One is complexity. For example, if you have a highly nonlinear model, if you have a very high dimension or very large scale of a network, So this kind of scale, dimension, nonlinearity brings challenge, brings complexity to your design. Another group of challenge comes from things related to performance. Say you are not only driving a system from A to B, you're driving a system from A to B, and you want to at the same time guarantee some performance, like minimize or maximize a specific performance function, or you want to guarantee global or semi-global convergence or stability, right? Another category of challenge come from real-time decisions. So you want to not only do the job that request by the whatever the application description, but you want to do it real time based on online data collected from the dynamic environment. So you preferably you have a relatively simple feedback law that requires minimum or at least affordable computational load for real-time computation, right? So now when you have a control system design problem, now you can, so among these three categories of challenges, okay, you pick only 2 out of 3. You pick only 2 out of 3. If your problem have, faces 2 categories of a challenge rather than all the 3, I think I'm pretty sure to say that you can find some existing control system design methodologies in control theory that you can solve the problem. Probably more than one methodologies, because control theory has been developed for all these years, many decades, with a very successful record of real-life applications solving challenging problems. Okay, however, if you have a problem that faces all 3 categories of challenges simultaneously, okay, you have, so the problem has very high dimension, highly nonlinear, and you want to guarantee some performance function to be maximized, and you want to do real-time decision-making, you want all, okay? Well, as I said, the control theory has been developed with very, successful record of a real-life application. You may still solve the problem using control theory, but I'm not so sure. So I think that for many problems where you have high dimension, you have you want to guarantee performance, you want real time, it can be difficult, if not impossible, in many cases. So then the idea is that can we combine control theory with the deep learning? So control theory mostly we do design based on some kind of model. The model does not have to be perfect, right? No model is perfect, so you allow some uncertainty, but more or less you have some kind of model. Then control theory is very powerful to guarantee performance, and then the feedback law can give you real-time decision making capability. However, oftentimes it suffers the curse of dimensionality. That's a terminology coined by Bellman. Basically, it describes the phenomenon in which your design or the solution, its complexity increases exponentially with the dimension. So that's a challenge here. However, deep learning has a reputation of dealing with high dimension or huge data sets, right? Successfully, we have so many successful applications using deep learning to deal with high dimensional data. But of course, guarantee performance or generalization or validation can be challenging. So then the idea is that let's combine these 2 and take advantage of both. I call it model-based data-driven, but this is not a new idea. So you'll see that there are many people working on this kind of idea, okay? This is nothing new, although people use different terminologies. Here I call it model-based data-driven, but some people more toward model-based side, and some design lean toward more data-driven, okay? So for example, let's talk about optimal control and HGB equation. Say, okay, you have a optimal control problem. The theory is that, in the following control theory, if you can solve the Harmony-Jacobi-Bellman's equation, HGB equation, then it leads to a simple feedback law And the feedback law can, you can use that for real-time control and then to guarantee, optimal performance, optimal in the sense of minimizing or maximize a particular cost function. The problem is that using traditional numerical method of solving HJB equation, the complexity of the problem increases exponentially, so it suffers the curse of dimensionality. So using this one as example to discuss the model-based and data-driven approach, here are some papers. Once again, there's no way, even for this narrowed down topic, I cannot give you a complete list of papers, impossible. You can see that the publication goes back many years ago, and also all the way to fairly recent, right? So that's something. There's no way I can give you a complete list. So I just list a few of them. We'll discuss some of them. For example, let's see this work of Tassa and Riz. Well, I don't know why there's a screen. The screen is let's try this one. Oh. Okay, I don't know why the screen has a scratch on it. Okay. Yeah. Anyway, so okay. In this paper of Tassa and Arias, they deal with a equation, optimal control problem like this. And this problem has a control system where X is a state and U is a control input. If you can solve the HJB equation like this, then you can find a control law. So the idea is that how to solve this one when dimension becomes higher, and then so in this approach, they actually approximate the solution, the value function that solution of HJB equation we often call it the value function. They use a feed-forward neural network to approximate this value function. Then the parameter in the neural network is trained to minimize a loss function. Loss function is based on the residue of HJB, the square of a residue. That's why the name least square solution with neural network. Okay, so they call it the least square solution with neural network. And then they applied this approach to some examples where the state space dimension was 2 and 4. They don't look like high, but I mean, believe me, if when you solve PDE, if you have a 4 state space dimension, that's not low. Okay, it's not very high, but it's not low either. So that's as I said, there are a long history of work in this direction. This is one, more than 10 years ago. Relatively recently, there are a group of people like Weinan and Han and Jensen. They actually published a sequence of papers using neural network to solve high-dimensional PDEs, including HJB equation. For example, this semi-linear parabolic PDE. This is a PDE that associated with optimal control of stochastic systems. Okay, and then to solve this PDE, actually, this type of PDEs for stochastic optimal control, it's a characteristic is associated with the forward and backward stochastic differential equations based on Brownian motion. Then this is a discretized version, so they can generate the sample points randomly. And based on the characteristic, and then here they are in this particular paper, they have a sequence of papers. In this particular one, they actually approximate the gradient of the value function by neural network, and then they train the neural network so that it minimizes the loss function based on the boundary condition and time condition, because in this differential equation you have the terminal time condition. So that's loss function. So in this paper, they solved HJB and Allen Kang equations. The dimension they push it to, the example they tested goes to 100 state dimension. That's a very high, it's hard to imagine you solve a PDE using traditional numerical method for this kind of a space dimension. Then that's another paper by a relatively recent paper, by Sirignano and Spilopoulos. Here they call the method DGM. That means the deep glerking method. Okay, deep glerking method. And in this paper, they deal with a family of PDEs. Here, L is a differential operator. Then you have initial condition and a boundary condition. Then they form a loss function that depend on the residue and the boundary condition and the initial condition. Then they approximate the solution by neural network. Then they train neural network to minimize loss function. In this paper, actually, they proved a universal approximation theorem for a family of second order partial differential equations using neural network. Basically, it guaranteed that any solution we under some wild postness assumptions, any solution is the limit of a sequence of a shallow neural network approximations. And then in examples, they tried, HJB, some low dimensional ones to make sure this is accurate. Then they tested a PDE based on stock price dynamics. Then they tried different situations. The space dimension goes up to 100 and 200. So that's that's another paper. Also, relatively recently, a group of researchers, Risi, Padakaris, and Kanyadakis, they actually published a sequence of papers. This is one of them, where they called it physics-informed neural network. The physics-informed neural network is based on the model, which based on the physics. But in this work, different from the previous ones, they actually deal with a solution of a PDE at the same time, identify parameters in the PDE simultaneously. Okay, so you assume you have parameters, then you have a PDE to solve, where this the residue of the PDE, but inside residue, they use neural network to approximate the function U. So as a result, this is it's not a traditional neural network, and they call it physics-informed neural network. And then they try to train the neural networks to minimize loss function that based on this part actually is something based on the known data, like either measured or based on boundary condition. And this is the loss function based on the physics-informed neural network. So that's so in this example, they tried the different type of PDEs, and where they identify, like in one of the, for the case of Navier-Stokes equation, they actually solve a equation with 2 space dimension and 2 unknown ones. So identification and the solution of a PDE simultaneously. So those, so that's, now this is my paper with my my collaborators, Qigong and Nakamura Zemara from UC Santa Cruz. In this paper, we use this so-called adaptive deep learning. Okay, so I may spend a few more minutes on this paper with a little bit technical detail because it's my own work. In this approach, we highly integrate both control theory and deep learning together. The idea is this: say, suppose you can generate the data for your supervised training. So here is an optimal control problem. You can generate data. I will talk about how to generate data later. Okay. So let's say, suppose you can generate data at any point you want in the state space. Then you can generate data for the training of your solution of HJB equation. Then you can generate data, because you can generate data at any point you want. Then you generate data to estimate the error. If so empirically, you check the error. If the error is not, you're not happy with the error, then you can actually go to this loop of adaptive sampling algorithm. The idea is that when we generate data, we generate not only the solution, also the gradient. So for example, if you have a surface you want to learn, right? Input, output, the relation you want to learn. Around the flat region, you don't need many data points, right? But around the region where the function change a lot, you need more data. So the gradient gave us information where we should focus on when we try to generate more data. So this is the idea of adaptive sampling. So we try to actually generate more data, focusing on the region where the gradient is high. Then you do another loop, training, validation. If you're not happy, then generate more data, and so on. And finally, you got an error that is within the tolerance you want, and then it results in a feedback law. You can give the feedback law to the system for real-time control. Okay, so that's a so this is archived in this paper, but actually just a revised version of the paper was just accepted a few weeks ago, accepted by SAM Journal on Scientific Computing. Then the question is that how to generate data. So data is essential here. Is but now when we generate data, we take advantage of our knowledge about numerical optimal control. So that's why I say this method highly integrated control. We control design methodologies with deep learning. So basically, in computational optimal control, after decades of research, we have many methods that can compute the value function and its gradient at the selected point. Okay, then you might say, hey, you already have, you already solved that HJD. Why do you need a neural network? Now here is the problem. As I said, we want to face all three categories of challenges, right? So numerically solving the optimal control problem is doable, but if you have high dimension and a highly nonlinear problem, it's not so easy to guarantee its convergence. It's not so easy to make sure the computation is fast enough. Sometimes there are always some points that it never converge, right? So, however, for the purpose of offline computation and neural network training, if you have 1 or 2% bad points where the computation diverge, it's okay. But you cannot do that real time, right? And also, if some points take much longer time to converge in the computation, that's okay for offline, but not online. So idea is that you move all the challenger part of computation, like the problem with high computational time, or problem it's hard to guarantee for some points to converge. This kind of risk and the computation load is moved off to offline computation. Then after the offline training, you get a neural network. This neural network you can apply to real-time feedback control, because the computation of neural network is fairly simple and fast. Okay, these days people even design hardware to do that computation. It's just very fast, right? So that's the idea. Okay, so for offline data generation, we archived some results here. It's a survey of some existing numerical method in optimal control that we think are appropriate for the purpose of generating data. One property that we really like is called causality-free algorithm. Some numerical method, you need causality. For example, you need a grid point, like a finite difference, right? So you to compute the value at one point, you need the value of the function at a nearby point. So this is not causality-free. So for causality-free method, you can compute this value at any given point, okay? It doesn't rely on value at nearby point. Because it's causality-free, you do not need a grid to solve the problem. So you have opportunity to, you have a hope to push the idea to high dimension. And also because causality-free, you can generate the value at relatively arbitrary point. Then you can target any region. Say I want more data at this region, that I just target this region. I don't have to swipe the entire region like we using grid point. solution, right? So you can find data at target in targeted regions, and because causality is free, you can fire up many CPUs or GPUs compute the solution at different points simultaneously. So it has perfect parallelism. Okay, and then so things like that. So we think causality free is very useful property for generating data in this model-based deep learning design algorithm. So once again, so that's a paper summarizes some computational optimal control method that can be used for they are causality free. Now here's the one that we use in the paper I mentioned before on the adaptive deep learning. In this adaptive deep learning, we generate data using the following way. So for some problems you can convert that problem into a Pontryagin maximum principle. That is ODE of Hamilton dynamics with two-point boundary value problem. That is, you know the initial state and then you know the final state. Then you try to solve this one. So two-point boundary value problem has a very bad reputation of convergence, right? It diverges, okay, especially if you use a shooting method. However, initial guess is very important, okay? So if you have a good initial guess, actually it's not so bad. What we did in that paper was to say, this is your final time, okay? If the time interval is long, it's hard to make it converge. So we start from a very short time interval. Very short time interval is so short that a constant initial guess will make it converge. But then after converge, the solution, you stretch it to a slightly longer time interval, use that as your initial guess to worm start the search for a solution of the two-point boundary value problem. Then you stretch to longer and longer. Finally, you stretch to the whole time interval. So that's what we call the time marching. Okay, this method is kind of slow, right? However, the nice part is that you do not need to worry too much about the initial guess. Okay, so there are some points it does not converge. It's okay. Majority of the points it converge, and then if after you generate a few points in the example, we generate only 64 points sample points. Then we train a neural network, and this neural network of solution is not accurate, but that's good enough to generate the initial guess to worm start. So you see that's two phases. The first phase we use a traditional optimal control methods to Pontryagin maximum principle and time marching to generate a small data set. Then we train it using neural network. Then we use neural network to worm start to generate more data. So even this data generation phase is already integrated with deep learning and traditional control methodologies. Then after after we do the training, so the neural network worm start, they can depend on the parameter you choose, it can push it to pretty much 100% convergence. Okay, so then we generate more data, right? So that's the data from one example here. This example in that paper, that's the rigid body, satellite attitude control driven by momentum wheels. So that's a standard format of the dynamic system. It's highly nonlinear with a 6 state dimension, the Euler angle and the angular velocity. And then here is it's a quadratic cost function. So for this problem, actually, we generate data. We tried this adaptive deep learning method. So we compare it to a sparse-based approach that I did with Lucas Wilcox a few years ago. In the sparse grid based approximation of the solution for the same problem, we need about 45,000 sparse grid points. But here we use 4,000 grid points to train a deep neural network. Not that deep, about I think we used, I believe, 6 layers, each layer about 100 neurons. Then this solution can beat the sparse grid that use 45 grid points. If you use adaptive deep learning, then we reduce the sample size by about half, about 2,000 grid points, we can do equally well with the fixed random grid point training. So this in the same paper, we tried some other examples, like Berger's equation. You discretize it using a spectrum method. We push that optimal control problem goes to the space dimension 30. We showed that example too. And then this approach, because we can generate data, so you can not only train the neural network, you can empirically test the error. So you can empirically validate the solution. And you can choose even focus the region to validate any region, target region. You want to make sure your accuracy is high in a particular region. Then you can target that region to generate data because you have the causality-free numerical method to generate data. In a related work recently archived by Ezel, Ostak, and Martins from European Space Center, they actually solved the problem of interplanetary transfer of satellite. Basically, that's orbital transfer problem for satellite or space systems, where they deal with the problem of state dimension 7, then using also causality-free data generation, but their causality-free method is based on a backward propagation rather than the two-point boundary value problem that we solved in our paper. But still, they share some similarities between these two satellite examples. So that's then there are many other papers I don't have time to mention, but that's just a few papers that you see relate to optimal control. But there are just so many more questions in control theory. They all suffer the curse of dimensionality, okay? For example, when you do output regulation, you need to solve a PDE, which we call FBI equation, okay? So this equation, when it's highly nonlinear, high dimension, you cannot solve it using traditional numerical method. Back, more than 20 years ago, people tried ideas of neural network, like this paper by Jie Huang and Steve Yao. So they actually try to solve the problem using neural network. And also recently, the work of Lars Grun, he used neural network to solve so-called Zuboff equation. This equation, if you can solve it, it's great. You can find you can find the optimal function to guarantee stability, and you can even find the domain of traction, right? But that's very difficult to solve, this PDE. Lars tried to use neural network to solve these PDEs. And there are so many other problems. H infinity control, differential gain, mean field control. All these fields have problems that suffer the curse of dimensionality. And I'm sure there are people doing research using neural network or deep learning to solve these problems. So it's a huge, I think, area that there are a lot of opportunities for everyone. Basically, model-based and data-driven. We probably can see hope for problems that we probably cannot solve using traditional methods in control theory. Okay, that's another thing I don't want to mention too much, but in the same direction of control and the data combined together, that's the reinforcement learning. This is a field has been studied by many people for many years, okay? The idea is also to face 3 categories of challenges: real-time performance, and now the complexity is more focused on large uncertainty or even partially known, partially unknown dynamics model, right? So this is a field I'm not such an expert, and I did not do much research, although I had some paper on that with Frank Lewis. But anyway, I just gave you see that this is a field you can find textbook from published many years ago. So these are some short descriptions of the idea of reinforcement learning in the books of Suta and Bardo, and here in this paper, a survey paper of Frank Lewis and Kiramasi and their co-authors. Well, this paper is more of like optimal control flavor. Okay, so that's anyway. I will not spend too much time on this, but that's in the same direction of control and data-driven, idea. So let's go to the second category of subjects. I call it control theory for deep learning. How control theory or in general dynamic system can help us to improve deep learning or explain deep learning. Once again, that's the Wei-Dan and Jiqing Han from Princeton, and also authors Li and Hao, I think, from Singapore. They published a sequence papers lately related to explain deep learning from the view angle of dynamic system and optimal control. Actually, if you look at a neural network, layer after layer after layer, it actually is a dynamic system, right? It's a discrete time dynamic system. So if you formulate that neural network as a discrete time dynamic system, then your loss function, suppose S is the number of the data, then the data gives you part of the loss function. Sometimes the parameter in your neural network have to be regulated. So you have a regulation term. So then you put them together, you see that this is in the form, kind of standard format of discrete time optimal control, right? If you take a limit of the sample, push it to high dimension, then it can be, it's kind of a approximate version of this continuous time version that is a differential equation with, this loss function becomes the expectation of a function that is, in the form of mean field optimal control. So for this kind of thing, I mean, in control theory, you actually have a lot of theory results analyzing optimal control problems, like punch-arcing maximum principle. What does that mean for training? And then numerical method of punch-arcing maximum principle, like a successive approximation. I believe in this paper, they tried successive approximation to do the training. And also you have HDB equation and viscosity solution. What does that mean for the training? So those papers address these questions. So that's one group of work. Now, this is another group of authors, Haber, Rosato, and Chang. In their work, they actually considered the so-called ResNet, residue net. Some people don't use H here. It looked like this, that's ResNet. But with H, it looked awfully similar to the Euler discretization. So it's naturally linked to the ODE like this, right? So the ResNet can be associated with some kind of ODE system. Now for ODE system, we know a lot of things about it. We know it's a stability, we know it's a reversibility, we know it's well posted and so on, right? So in these papers, they actually try to design neural networks, design ResNet that has certain property, and then such as stability, reversibility, or some properties inspired by Hamilton dynamics. So they can take advantage of the known properties ODE to design residue nets. So that's this kind of thing goes back many years. If you go back almost 30 years ago, you see this survey paper by Sontag, discuss neural networks and control theory. For example, this recurrence nights, right? That's something like this discrete version, continuous version. It deals with the data which has comes in as a time sequence, and then also some other survey papers, long time ago about related topics. But in this particular paper of Sontag, he actually proved this universal approximation for control system, for any control system with some smoothness assumptions. It guaranteed that the recurrent nets can approximate this. If you can find some mapping back and forth, you can approximate this control system, not the state, and also input to output relation to arbitrary accuracy. So that's kind of a universal approximation theorem But there are other things, we know controllability, we know observability, we know identifiability of this kind of, if you treat them as control system, then what does that mean for the learning, right? So this kind of thing, you go to these papers almost 30 years ago, you see what happening at that time in this area. Okay, so that's kind of fascinating, I think, to see so many people for so many years working on related subjects. Now let's move on to the question, why deep learning work for high dimensional problems. This question, as I said, is a huge question. There are many work. Once again, there's just a few papers. I think I will go through a little bit. I will discuss a little bit of this paper of Baron. His work has a lot of influence. And then also, here are some, one paper by Wina and one paper by Cannon. They are survey papers, so you can get some ideas about other people's work. Then I will talk about some paper by Paul Mahaska and myself. So this is a paper. Once again, Baron had many papers. This is one of them. It's a very interesting result. Here in this paper, you assume that your function, you have information in and information out, called it F, and then you have from RD to R. Assume this function has Fourier representation, and assume that its Fourier transform have some kind of a first moment is bounded. Okay, under that assumption, it can be proved that under any measure, the L2 norm of your neural network, so there exists a neural network approximate F, and then the L2 norm of the error is bounded by a function like this. Okay, the interesting part is that this here n is a number of neurons. You increase the n, then the error reduce. So the rate of convergence is independent of D. Okay, that's very interesting because that means your problem, the rate of convergence does not suffer the curse of dimensionality. You choose any D here, the rate of convergence is a 1 over square root of n. Basically that L2 norm, that's a square L2 norm. So the rate of convergence is bounded by 1 over square root of n. So that's independent dimension. So you do not suffer the curse of dimensionality. So that's very good, right? However, if you look at the other part, the parameter, their papers show that these parameters are related to D and they can grow exponentially. So the overall approximation is not free of curse of dimensionality free. It's not, it may still suffer the curse of dimensionality, but still that's great that the rate of convergence is independent dimension, right? But the other part can still depend on the dimension. Now, in a different approach by Poggio and Mahaska, they have, once again, they have a whole bunch of papers. Okay, that's two of them. In this paper of 2017, I believe, and other papers too. So they consider the function as not a black box of input output. Okay, they treat it as a directed acyclic graph. So you have a graph. Each node in the graph is a function of relatively simple dimension. Okay, and then this graph gave you some information that can tell you the neural network approximation. So, for example, in this theorem, based on some smoothness assumptions, they can prove that for the function from RD to R, the neural network approximation is bounded by arbitrary accuracy, but then the complexity or the number of neurons in the network sometimes is called complexity. So the complexity is bounded by something like this. Okay, you still see exponential growth here, okay? Exponential relation here. It sounds like curse of dimensionality, okay, with the rate of convergence. But however, this D is not the dimension of the overall function's input space. It's a dimension of each node. So in other words, if each node in the compositional function have low dimension, then this approximation does not suffer the curse of dimensionality. Okay, I think this is very interesting because it's not like, it does not treat the function as a overall input output black box type of thing. This treated as at least, you know, a gray box, in the sense that you know the some structure about the function in terms of DAG, okay, the graph. And then the input dimension of each node gave you the rate of convergence. Okay, so if you can increase the number of nodes, you can increase the dimension, overall dimension of the problem, as long as these nodes are, you know, the input dimension of each node do not increase, then the problem does not suffer the curse of dimensionality. Okay, so now in the same line of research, recently we archived some results. In this paper, we make the assumption that it is common in mathematical models that complicated functions can be represented by composition of relatively simple functions and have low low input dimensions. Okay, now rather than DAG, we found that you do, you know, all the DAG you can find the layers, you can layer them. So the layer structure turns out to be very important too. Okay, so we deal with DAG that has layers. Okay, layered DAG. Now we try to address the question that, you know, for example, here you have a seed that you don't know, right? If you do layer DAG, we found that, so we try to address what is overall error, not only the rate of convergence, the overall error. Does that suffer the curse of dimensionality? Okay, and then also we want to treat not only functions as input information in, information out. We want to deal with problems associated with the dynamic systems and optimal control altogether. Okay, but before we go there, let's talk, you know, spend another minute or so to talk about the compositional function. Composition versus the projection. Now, when you have a function, you want to represent the function. A traditional way is to represent function using projection. For example, power series or Fourier series. Now, you know, in Fourier series, you represent a function by Fourier series. That means you project the function to finite dimensional orthogonal subspaces. Okay, now you add two Fourier series, you get a Fourier series. Okay, so I say, you know, basically each frequency, you just add the corresponding terms of the same frequency together, right? So you keep the format of a Fourier series unchanged. So we say that Fourier series, or in general projection method of representation, typically they are closed on the linear combination. You do linear combination of Fourier series, you got Fourier series. Okay, however, Fourier series is not closed on the composition, right? Because if your sine function at certain frequency, you compose with a cosine, it's not in the immediate form of a Fourier series, right? So you have to reproject it again, right? So it's not closed on the composition. However, if you have a compositional function, if your function is represented by layered, you know, DAG as a compositional function, then composition of two functions, you just put the graph of one function in front of another one. So the output of G is linked to the graph of the input of F. Then you got a new graph that is still, you know, you don't lose the information of this component in your composition structure, right? So the compositional structures are preserved. So I say that compositional function representation are closed under linear combination. Okay, not only that, you see that in many, you know, dynamic system problems or optimization problem, you approximate your solution using iterative algorithm, right? Iterative algorithm is like step after step. You know, when you apply it to a particular problem, it is actually compositional function, right? It's composition function of many steps to reach the approximate solution. If you think about in this way, then all the iterative computational algorithm, when you apply it to a particular problem, they are compositional functions. So this representation can represent not only input-output relation, it can represent computational algorithm. And then that applies to dynamic systems and optimization. Also, of course, neural networks, they are compositional functions, okay? Each component now is a neuron, you know, a activation function here. So it's a special family of compositional function. And also, historically in the literature, this famous Kolmogorov and Arnold representation theorem says that any continuous function can be represented by two layers of composition of single input functions. And the number of these nodes are not large, okay? It's polynomially dependent on the dimension. So you see all these kind of justifications or items show that compositional representation function is interesting when you deal with neural networks. Okay, here I'm not saying that compositional representation is better than a projection representation. I'm not saying that, okay? Projection representation like Fourier series, power series, they are very useful, okay? Spectral method, people use that to solve, all kinds of mathematics problems. It's just that, I think compositional representation function is kind of special when you deal with neural networks. So it definitely worth effort to do some research on that, such as this paper I mentioned in this archive paper. In this paper, we gave the composition function layers, and then based on layers, we can define some features. Okay, so a compositional feature function has a compositional feature that has a dimension feature that's related to the dimension of each node rather than overall dimension. The volume feature, once again, it's not the volume of overall function. Here we use infinity norm and its derivatives depend on the smoothness and also the volume, or the size of the domain of each node, right? So we call it the volume feature. And Lipschitz constant for each node from the node to the final output, depending on its layer, then this Lipschitz constant is different. And then you have the largest one, we call the Lipschitz feature. Then the complexity feature is the total number of nodes. If you have more nodes, typically it's more complicated. So these are 4 features, right? Based on compositional features. Then that's defined by the structure of the function. And it turns out that these features actually define the overall upper bound, at least one upper bound of neural network approximation. So for the C1 function, there always exists a neural network so that its error upper bound is bounded by this error. Now, this is not associated with number of neurons in the neural network. So you see the rate of convergence can be still exponentially, can have an exponential relation. It sounds bad, but however, this power part here is related to the dimension feature, which comes from the dimension of each node, not the overall dimension. So you can increase overall dimension, but for example, you have a power network, you can have a 1 generator, 2 generator, 100, 1,000 generator. The dimension can increase, but each node is more or less the same. So the dimension does not increase. So for this kind of thing, rate of convergence does not suffer the curse of dimensionality. Then the rest part of the error is just a linear function of the feature. So it's not exponential at all. So that gives you the error, the interconnection between the error of neural network approximation with the compositional structure. Okay, and then because algorithm like Newton's method, it is actually a compositional function. So this algebraic framework we developed based on the compositional feature can be applied directly to some optimization problems. For example, this is the optimal control problem where you use discretized control, digital control, for example, and then you try to minimize the cost with a cost function per se. If the dynamics and the cost function has the kind of this kind of a compositional structure, then in a layered DAG, then we can prove that the optimal control can be approximated to arbitrary accuracy. Then the complexity is bounded by a function like this. The C function is a polynomial function of features, but it's too complicated, so we can write it down. But here I just put it as a constant, but that's a polynomial function of a composition feature of f and the cost. And then the rate of convergence is exponential. Once again, the exponential part relate to the actually the feature dimension feature of f and g in the graph. So it does not necessarily converge. It's just a dimension of each node. Okay, so you can apply the same framework of approximation theory to optimization. Okay, so that's this paper about compositional function and its neural network approximation with application to dynamic system and optimization. All right, I think it's time for conclusion. I think my conclusion is short or long, okay, it depends. The short conclusion is that, there are a lot more questions than answers, all right? You can see that there are just so many questions. It's just a partial review of some topics. You already see that there are a lot of, papers, some old, some new. But for long conclusion, you see that all these, there are just so many topics. I mean, they don't, all these topics do not have a satisfied, mature solution. And there are a lot of work that can be done related to deep learning and control and dynamic systems. So I think I just wrap up and stop here for questions. Thank you.
Okay, thank you very much. Any questions? Yeah, I saw an earlier comment from Eduardo Sontag, and he had, if you would like to talk.
Oh, okay. Yeah, Eduardo, thank you. Yeah, I mentioned some of your work. I'm glad you're here.
Yeah, it's nice.
Your work actually really inspired me. One of the, your work and We Know Us work really inspired me to go into the direction about a few years ago. So probably a couple of years ago. That's I'm glad you're here. Thank you.
Thank you. No, I enjoyed. Can you hear me? I'm not sure if I'm muted.
Yeah, I can hear you. Yeah.
Yeah, no, thanks a lot. I mean, it was a great talk. I mean, I really love the part about the warm start idea for the marching method. I mean, that's a cool way to use the, yeah, that's very nice. So, no, I mean, I don't really have anything to say. I enjoyed it. I just a very quick thing, as you said, I think in the 1980s, there was a huge amount of work on people trying to find feedback laws, including optimal control laws, but even just stabilization and so forth, and even control Lyapunov functions. I even had a master's student doing a master's thesis sometime in 1985 or so, using neural networks. But of course, I think that in my opinion, and you'll tell me if you think differently, I think that the big difference is now the availability of computational resources. That's, I think, what makes, I'm not sure that in that particular question, there's that many new ideas. I think it's more a fact that, that we have the computation to do it. So that's, so I'd like to hear your comments on that. But just quickly, a couple of two things. You didn't talk really very much about sparsity, and you also didn't talk about what I think is a key issue, which is overparameterization, and why do things work so well in the overparameterized case. Now, maybe some of the compositional stuff sort of can help understanding that, but it would be interesting to hear a little bit more your point of view about that. And then one last thing, what I had in one of the chats was there were these results. Oh my God, this was maybe in mid-1990s. I don't remember, that we got generalizing on these results to both L1 and L infinity rates of approximation. And that could be interesting because of lasso and things of that sort. You get more robust things. Things are very complicated because you end up with non-smooth Banach spaces. So there's lots of really interesting technical issues. I think that sort of was all forgotten. I don't think anybody ever did anything with that, but it would be cool to, maybe somebody in this audience will say, hey, let's try to see if we can use that and develop it further. I certainly did. Anyway.
Yeah, I think it would be nice to have this L1 training of neural networks. I'm not sure how to do that, but I think that's definitely
absolutely
interesting.
Yeah.
Like you said, it will be lasso, so we may get like a training of discovering the architecture of the neural network from the data. So where some weights would end up being zero automatically. I'm not sure.
Yeah. Well, these were different, right? These results were more like Andy Barron's results. They were sort of given rates of approximations that were, 1 over square root of n, whatever it was. I forget what we got in our case was different power. But it's more theory, but very similar. Well, it was directly motivated by Andy's work. I mean, we read this paper and said, hey, maybe L2 is not the most interesting thing to do in many problems, and infinity is much more important in terms of robustness. So anyway, just mentioning, it would be interesting if somebody ever picks up those papers and says, hey, we can do much more with it. We just barely scratch the surface. But what about, my question about sparsity, I think, was the main question, and over-parameterization. That's the question.
Yeah. Okay. So I think well, before that, I mean, one thing you mentioned, I cannot agree more, is that, one big difference here, maybe one of the main difference here, is that we have the computational capability, so that we, it kind of, for me, it's a big motivation or to move in this direction, because, I mentioned this, you mentioned also this type marching. I did not mention that in the sparsity approximation paper, we use parallel computation, because you need 45 tens of thousands of grid points. So actually we fire up about 500 CPUs to do parallel computation. 30 years ago that was hard, if not impossible, because now the school has this parallel computer used for free. And then in the recent paper, Tanavi, the co-author. Actually, by the way, I mean, I gave the credit to Tanavi for his for this neural network wormstar in our joint paper. So he used GPUs with tens of cores and to do the computation. So this kind of thing. Not only that, solving these, like for last, couple of decades, you see the method like pseudo-spectral method, right? And even the 2-point boundary value problem. These methods toward mature, so you can use them to generate data. This kind of thing cannot be imagined, 20 or 30 years ago. So I think that's really something changed a lot, actually, changed the landscape of this of these problems. Sparsity. So we have sparsity is something I tried it for some sparsity grade specifically for this data-driven approach. It's very interesting because it's structured. So you can actually have quite, and it has the theory about error upper bound everything. So that's good. You have confidence when you have a solution, right? But the challenge is that you mentioned later, when you have non-smoothness, everything, sparsity can be a kind of, sparsity has a structure. If your non-smooth thing happen to be away from that structure, it causes a lot of trouble. But of course, adaptive sparsity could be something, but I never got a chance to try that, right? Over parameterization, I don't want to pretend to be an expert, so I don't have much comment on that. Although I admit it's a very interesting question. Just like in Paul's paper, he asked the same question. So why over parameterization always work, or not always, at least work very well in many empirical examples? Why? I don't have any study, and I admit that's an interesting problem. And you mentioned L1, L2, or L infinite norm. Actually, I did not emphasize, but actually in my recent paper on the compositional function, that's another reason I like it, is that I can prove the theorems using L1 norm, okay? Because in control, the recent simulation shows that you have very nice L2 norm error bounded, but there are some bad points. You tried thousands of times or tens of thousands of times, there are some bad points where the control pumps up, then goes, diverge actually. So L1 norm is it can avoid, if you can guarantee, of course it's hard, but if you can, it avoid this kind of tail event. We call it tail event, low probability, but it's there. It can be bad, right? So it's hard to capture those kind of tail event using L2 norm. We have some study, and also non-smoothness. It has to be other, the theory we have so far based on smooth activation function. So what does that mean? The composition function based on non-smooth functions. That's a big question. We're interested in that, but haven't published anything yet. Okay.
All right, thank you. Any other questions?
I mean, I could do a little follow-up, but
Yeah, sure, yeah, please.
no, but let other people. No, I want other people to ask questions. I don't want to.
Yeah, but no one is, no one.
Well, no, I mean, I was just a comment. When I said about sparsity, I wasn't talking so much about what is very nice, you know, the sparsity in terms of the adaptive grids and so forth. I was talking about something completely different. I was talking about sparsity in the architecture, namely the in degree or the out degree of particular neurons may be limited, and that actually might give you, you know, a lot more structure, a lot more learnability. I think that you know, that's more what I meant. Yeah, that's more what I had in mind. And also, you know, yeah, and in terms of over-parametrization, there's of course, you know, a lot of work going on right now, like you said, and I think Peter Bartlett's paper in PNAS this last year and that kind of thing, where you put some sort of regularization with some of the, you know, the L2 norm of all the weights or something like that, that actually gives you an incredible amount of generalization ability, at least in theory, and in his case only in linear, basically linear problems. But it sort of points the way to maybe understanding why over-parametrization is in fact good. But anyway, I just wanted to get comments on that.
Yeah, I think that's right. Sparsity of the neurons. Okay, that's why I'm so excited about the using the DAG to represent, or layered DAG to represent the function, because in the paper that proved the, you know, composition function error upper bound, if you get into the detail of the proof, actually the neural network we use to prove that error upper bound has similar structure as original compositional structure. So this compositional structure has, you know, as obvious sparsity structure over there, right? So you don't, each neuron does not have the you know, input from every neuron in the previous you know, layer. It's actually sparse, and then actually the neuron we use to prove the error upper bound has the same structure of sparsity in terms of, you know, sparsity of a parameter. Yeah, so that's a good, you know, good that you asked a question, so I can explain that structure. That's another reason we got very excited about the compositional representation functions, because they inspire you know, the sparsity structure of the parameters in the neural network design. Yeah.
All right. Any other questions?
Yeah, it's a long talk.
Yeah, I think a lot to digest.
So people get tired probably.
Yeah,
and then it's pretty late in some other places.
It was a cheap ticket to get to England.
yeah. It's almost a free ticket, you know.
Yeah.
But still nice. Appreciate that. Yeah.
Teleportation.
Yeah, by the way, you know, there was one thing that it's interesting is that a lot of, like, this paper I had, there was a big workshop at the Newton Institute in Cambridge in the early 90s, I think it was, I forget now, where we presented a lot of this stuff. There was a lot of discussion about all this.
Oh, okay.
Oh,
yeah.
Okay.
Yeah.
So I would
I mean, it would be nice. I mean, if Professor Zondag, if you want to give a talk or to summarize all this stuff, I mean, I'll be happy to host you. Just let me know if you would like to do it. I mean, I realize that it's a lot of work, but if you would like to, it will be an honor. Yeah.
Yeah. Give me a little time. I'm so crazy with teaching, and I have a problem with my voice right now. So
but I think it will be definitely nice to come back to these old results and then see how to resurrect them in a way.
Well, I think Wei invited me to give a talk at a SIAM workshop that he's doing, where I'm supposed to talk about some of these old controllability, observability, identifiability approximations. So I'll give a little survey talk right there.
All right. Okay. Yeah.
The SIAM meeting in December.
Okay. All right.
Yeah, that's an invited talk. That's in the mini symposium. Bomedian, you will be one of the speakers there too.
Yeah.
So
okay. Yes.
I think that's nice.
We get to see me there.
I still remember that back in 1991, when I was a fresh PhD graduate as an assistant professor in WashU, AFSR hold a 91, 92 hold a PI meeting in St. Louis. That was my first PI meeting in
the aerospace company, right? right? We were at the Grumman or something, or not
Yeah,
Grumman, Donald
no, it
Douglas.
was in Warshio actually.
Oh, because I
think
went
you
to an,
talk
yeah.
Yeah, Eduardo talked about the neural network. That was, you know, that's how long the literature. I think it's for especially newcomers. It's nice for them to see the work back, like you mentioned, 80s. I did not go back to 80s. When this survey here in this presentation, I only go back to your work in early 90s. But then I think it's nice for newcomers to see the see the all the flow, a long time flow. So that's of this topic is very rich literature. It's very interesting and rich.
Yeah, it's like you mentioned, it goes all the way to Kolmogorov, right? It's about 100 years ago.
Yeah.
Yeah, I would. Well, yeah, I would say more perceptrons, and and Minsky and Papert. I mean, maybe I would give a little more of the credit for the start of the field there in terms of theory. Kolmogorov, I think, is more of a curiosity.
I see. Yeah.
Yeah.
That's my view.
Great.
Yeah.
I'll be more than happy to hear that. Yeah. It's
well, the perceptrons book, right? It was in 1967 or so, sort of killed neural networks, right? I mean, you may not remember, but in the mid 70s, neural networks was considered to be more important than the atomic bomb. I mean, this was something that the Navy, I think, had. One of the directors of the Navy said, this is a future neural networks, and it's more important than the nuclear technology. I remember the headlines. And then between the British report, and the book of Papert and Minsky, the field sort of went into the winter, the neural network winter. The winter was coming. Anyway, but of course, then the computational resources, being able to do multi-layer networks by gradient descent, AKA backpropagation. That thinking of things that way, that was definitely Hinton, other people that was they sort of popularized the game, but without theory.
Well, actually, 70s, I think Japanese government poured in a huge amount of money to do the expert system, and the industry got the jump on that idea too.
Right. Well, more expert systems and neural networks, but no, neural networks, I would say, was big in 1960. Was killed around 1967, then again came up in the late 70s, the mid 70s, and then the report. What was it? The famous? I'm sorry. What was the famous mathematician that wrote the report, saying that there was this. I remember the phrase "artificial intelligence and natural stupidity." I remember that was a headline.
Oh, really? Okay. I don't know that. I don't know that. Okay, I will try to find that.
I was a grad student, and this was a big. I wrote a book. I wrote a book in 1969 on artificial intelligence, and I described there, a little bit of neural networks. It was 1970, I think, was my book or something like that. 71 maybe. It's on my website. I scanned it. It's in Spanish though. It's in Spanish, but it was anyway. Anyway, cool. Thanks for the talk.
Oh, thank you. And thanks to Bomedia for the invitation.
Yeah. Thanks again for coming, and it's a very nice talk. And then I think Eduardo, it would be nice to have a talk from you as well in this series, where you could summarize all this stuff. Okay, so let's thank the speaker again.
All right, thank you.
Thank you very much
for being here. And for some people, it's pretty late already. All right. Okay.
Okay, thank you. Take care. Yeah, take care, everyone.
Okay.
Bye-bye. Bye.
Bye-bye.